Okay. So before we talk about how we can resolve those problems, the problems that we saw in the previous slide, let's talk about, different kinds of numbers, right? There are two kinds of numbers out there. There are exact numbers, right? Number of students in this class, that's exact, right? We can't have, if we have 250 students, that's 250 students. We can't say we have 249.56 students. Not going to happen, right? Number of hands, number of legs. So those are all exact numbers. And somehow those numbers have maybe infinite precision, a different kind of quality about them, right? There is a sense of absoluteness about those numbers. And that's why they're called exact numbers, right? You also have unit conversion factors in the formulas, like 1 meter equal to 100 centimeter. That number of 100 is an exact number, okay? Within the same unit system, the conversion factors that you use are exact numbers. But if you go from one unit system to another, like USCS to SI, the unit conversion factors you use are not exact numbers. Okay, so this is the example. So if you go from 1 kilogram to pound mass, and it's 2.2046, 2.2046 is not an exact number because you went from one unit system to another. Okay, and that's the general convention. So in exact numbers, we talked about that. Any value that you measure using some sort of measuring scale or you compute are in general in exact numbers. Okay, so they don't have that, the kind of quality like exact numbers have. Okay, so we're talking about the quality of the number. How do we measure the quality of a number? Whether it is computed or whether it is measured, right? And there are two attributes for the quality of a number. One is the preciseness, how precise that number is, and the other is the accuracy. Now, a lot of times in our day-to-day conversation, we actually mix these two terms, right? When somebody says, hey, my height is 5 feet 7.67 inches, am I being accurate or am I being precise? Precise? I'm being precise? Oh, exactly. So accuracy will really depend on how tall actually I am. I'm saying I'm 5.678 inches. Definitely, I'm giving a lot of digits after the decimal, so it makes it look like as if I'm being very, very precise, but it may still not be accurate, right? I may be lying to you. I'm just giving you a large number to make it look like as if, there is a great quality in that number, but it may not be accurate, right? So accuracy and precisions are not to be mixed with. There are two different factors that describe the quality of a number, right? So what accuracy measures is the truthfulness. What is the actual height, right? What is the actual mass? What is the actual number? And how do you know what is the actual height? How do you know what is the actual number? There has to be some sort of known, trustworthy scale or a reference that you have to use to know what is the actual number. There's no other way, okay? So there might be a mass of 1 kilogram kept in some lab in Paris, right? The 1 kilogram is still defined that way. It's a known mass that is kept in some lab in I don't know, some part of Europe, somewhere, yeah, right, somewhere. I remember that in high school, but I don't remember that now. So it's somewhere there, and that's your reference. So if you really want to see if something has mass of 1 kilogram or not, if you want to compare the truthfulness of the mass, you have to compare it with that thing. Okay, so that's truthfulness. That's veracity. That's the accuracy. And accuracy is something that is not easy to verify. Okay? You just have to trust your instruments that are given to you and say, hey, I trust this instrument. It's not something that is rigged or has maybe deformed, right? For example, if you take your, 6-inch ruler, okay? You take your 6-inch ruler made of maybe wood, okay? Wood has very low thermal expansion. But if it is made of from another material that has a large thermal expansion and you use it in a hot area, it could expand, right? So your inch ruler has now become incorrect, right? No matter how accurate it is, no matter how precise it is, how many gradations are made on it, now it has deformed, it has expanded. So anything you measure from it is going to be inaccurate. It may be very precise, but it is going to be very inaccurate, right? So precision is something that depends on the measuring instruments, the instruments that you have, or the computer or the calculator that you have, which you are using to compute numbers, okay? So precision is easy to see, because it directly relates to your computation, your computing tools, and your measuring tools, right? So another example of precision is where you can reproduce something again and again. So if there is less deviation in measurements, you're being very precise. It may still be inaccurate, right? So this is the example of the bullseye, right? So if you're around the bullseye and you have a lot of dispersion, so you have very high accuracy because you're close to the bullseye, but you have very low precision because shooting here, now you're shooting here, now you're shooting here, right? On the other hand, you could be very precise, but you could be completely off the target. All of your data points are clustered together, so you have very high reproducibility, very high precision, but very low accuracy, right? So if, let's say, there is a calibration problem and you're doing experiments correctly, this could happen. So you have precision, but you don't have accuracy.